hey, let's start all over again. So I'm James Gallagher. I'm here from OpenDAP. Here's Miguel Jimenez. He's here from OpenDAP. And we're talking about this emerging idea of chunk manifests. And we're looking at common patterns, common problems, with an idea to ultimately think about forming an ESIP cluster that will address some standardization effort. And so that is the very brief introduction to what we're aiming for here today. I'm hoping that at least half of this hour-and-a-half long session will be you all talking about these ideas of what kinds of things would go into a standard, what sorts of problems have been discovered. I have a particular view about standards. I don't really think of standards as being tools for interoperability. I think of them as being functional design components that can be plugged into a larger system, and that can help further interoperability. But I really think about them as enabling developers by providing proven designs. We've got 4 speakers. 2 are remote and 2 are here. Ayush Nag will be presenting first. Then Miguel will present, and then Alexander Jelinek from the HDF group will present, and then Joe Hammond will present from Earthmover, and then we'll go into our breakouts. And in the Google Doc, I've enumerated, actually Miguel did, enumerated some points that can be sort of conversational starting points for you all. You can choose to form like one big breakout, or you might split up into 2 different groups. In general, I kind of think of standards as falling into 2 camps: content standards and format standards, and that might be a way that you also see those discussions. I think with that, we should just get started, unless you have any questions. Yeah. I probably do want to say that, yeah, because we've got a lot of established practice, I think. Yeah. So can we codify what we've already done and make it more easily accessible to other people? But anyways, with that, Ayush, are you ready to go?
Yes, yeah, I'm ready.
All right. And how do I get his slides up?
He's gonna do that.
Okay.
Just check if you're unmuted now.
I think you're ready.
Will you go to the Zoom? Yes, there it is.
Are you able to see the screen?
We can't see your screen yet, but we can see you.
Okay, yeah, let me fix that really quick.
There you go.
Okay, it looks good now?
Yeah, it does. That's great.
Okay, great. So, hi everyone, my name is Ayush. I'm going to be presenting today about an integration I worked on between Virtualizar, DMR++, and Earth Access. So I did this while I was an intern at NASA JPL. And if you want to reach out, feel free to message me on GitHub. It's my GitHub link below. So first, I'm going to go a little bit into the problem that I'm addressing here. I think most people are familiar with this problem, but in my specific case, I was asked to work on the SWAT satellite, which was recently launched in 2022. And that satellite produces a bunch of sea surface measurements, and the level 2 data set that it produces has a lot of granules, or a lot of data files. It produces many data files. So in just 21 days, it can produce like 600 files. And I think to date, in the 3 years it's been launched, 2 years, like 90,000 files. So if you want to load this and do analysis for scientists, just reading and joining a large amount of this collection, even in AWS, would take like 4 hours with Xarray, for example. Just because even though these have been placed into cloud storage, the netcdf format just isn't optimized for a large amount of loading and concatenation very rapidly. With this, exploration, analysis, and visualization are all bottlenecked since the loading is the first step. And this chart, which is I think a little bit old now, showing how the size of the NASA Earth data catalog is growing at a significant rate, and this problem will only get worse. So one solution to this, which I think most people here are familiar with, is ZAR, where we can have our data plus metadata together and store that in the cloud, and then have really fast access to large data cubes. Or an alternative is if we don't want to duplicate or we can't duplicate the entire ZAR netcdf archive, we could create these, we could use Kerchunk and create these metadata sidecar files and then tell Xarray to load this with OpenZAR, and we get a lot of the benefits of ZAR in this method. However, there's still some challenges with this approach because Podak would need to generate and maintain these little metadata JSONs for SWAT, but all of the collections that we want to enable this with. And also, the user needs to interact with these metadata files and knows how to concatenate them and understand, kind of Kerchunk API. So it's a little involved for the user. Um, However, I looked into another approach where we reimagined the same workflow, but using DMR++ instead. So DMR++ is a similar sidecar file that OpenDAP creates, or OpenDAP has kind of created the standard, and the DACs hold these files. And these can kind of contain almost entirely the same amount of information as the Kerchunk metadata. And so we can imagine this workflow where the user can use the Earth Access package to simply give a query. And since these metadata files already exist, we can grab the metadata files, parse them with virtualized ZAR, and do that same workflow where we tell Xarray to open it as a ZAR file. But instead of having created any new metadata files, we can just parse the existing format. And the user now has their data set ready to access right away. So that was kind of the work I did during the internship. I implemented this solution where I created a DMR++ to ZAR metadata parser, and that's been added to the virtualized ZAR package. And I also added two top-level functions for the user. So the user can just call earthaccess.openVirtualDataset or openVirtual multi-file dataset. And this is now in Earth Access, and you're able to try this out. So yeah, Earth Access has this top level integration here. So even finding the DMR files can be a challenge. So we don't want the user to have to think about that. You can just use these files, and this will search for the files and do the kind of parsing in the backend. And yeah, here's kind of the results of that integration. So now in just a few lines, you can say, earthaccess.search for data. This is a mere high resolution sea surface temperature dataset that Podak produces. So we can ask for 100 of those files and say open virtual multi-file dataset. We're working in a cloud environment, so it's even more optimized because we can just access the version of these files that live in the Podak cloud. And so in just 5.5 seconds, we have access to this 2 terabyte data set of high resolution sea surface temperature. And we can access it, work with it, analyze. And it's in an Xarray format. So some of the benefits of this approach is that this abstracts away some of ZAR and Kerchunk away from the user. So in the backend, this is doing all of that parsing and manifest logic, but the user doesn't have to interact with any of that because of this top level function. And Earth Access also handles acquisition of the credentials. So this is one of the overall benefits of Earth Access is the credentials movement. So now you don't have to find the DMR files. You don't have to get your temporary credentials to the for the DAC specific Earth Access. This function is doing that for you. This is doing on-the-fly reference creation. So this function call here actually found all the DMR files, parsed them, and then created the virtual data set and also loaded it for you to use, for you to do analysis with and work with the data. And the main big benefit is that this DMR++ is in use for all Podak datasets and many of the other DACs as well. So this didn't require any new DAC initiative yet, and this is working immediately with the datasets that support DMR++. And the parser is very fast. It only adds a few milliseconds of overhead per granule. So it's not adding too much for the user to do. Um, yeah, so this is kind of the solution that's been implemented. One kind of now like science case for how this integration can be used. So again, with the SWOT data set, can now work with large amounts of SWOT data and visualize and do analysis on them. So this is an example of where a specific variable had to be modified to apply like a crossover correction. One field needed to be corrected with a certain value, so we added two fields together and we plotted them. And now this is a dashboard with 200 million pixels of SWOT high resolution sea surface anomaly, sea surface height anomaly. So you can see now this is like global coverage of SWOT, which is normally very difficult to load, let alone plot. But now with this approach, we're able to um, get this large amount of data in our Python notebook and zoom in, and it's gonna just grab the regions that you need, and you're able to see SWOT's like internal waves that it sees. These are yeah, internal wave structures that the SWOT is seeing. So yeah, this allows users to modify data, do custom computations, and do subsetting analysis, all within a single notebook and really rapidly. And so some of the next steps of this work are to increase availability of the DMR++ files. In the next talk, Danny or Miguel is going to talk about the availability right now, what the current status of these are, how many collections support this. But increasing availability immediately allows this approach to work. If the sidecar file exists, then the user can access these files rapidly. We're also working on porting the parser logic to PyDAP instead of virtualizr, so we can keep some of the DMR++ specific logic in OpenDAP and PyDAP, and the chunk manifest logic in the ZAR kind of domains and libraries. And this work was done a few months ago, but there's been a number of recent enhancements with virtualizr and the new releases they've been doing actively, um, such as reading data with OB store and manifest store, new backends to access data more quickly, and using some new virtualizr, multi-file dataset opening techniques, group datasets, and creating ice chunk stores via Earth Access directly, which sort of Joe will can talk about ice chunks some more as well. Um, so yeah, that's kind of a summary of the work and where it's headed. And yeah, feel free to reach out or try it out on the GitHub. It's available right now, and there's been some number of discussions on the Earth Access repo. So yeah, feel free to check those out. So yeah, thanks for listening, and let me know if you have any questions.
Thank you, Ayush. That was great. I want to maybe give opportunity for some one or two questions for anybody in the audience who has anything to ask Ayush about his experience working with this metadata chunk manifests. Okay, well, I have a question for you, Ayush. So we're kind of here trying to have a little bit of a showcase, talk about the different options, and you kind of were part of your work here was kind of bridging the gap, and I wanted to maybe give you opportunity to talk about the pain points of trying to bridge the gap between all of these chunk manifests, or perhaps shared commonalities or places where you didn't see shared commonalities, as we're trying to potentially have these interoperable across many different APIs and everything. So do you have a perspective on that or experience?
Yeah, briefly, I mean, I think the technology of like accessing data is progressing really rapidly, but I think some of the data format and shaping is one of the big concerns. Like SWOT level 2, as I described, is in like these wide swaths, and some of them are uneven, like they're not exactly the same length. So then joining them with ZAR is like not possible. It's just because of there needs to be contiguous shape, right? So, and sometimes even with Mirror SST, some of the older files are chunked differently, which means that even this work cannot happen because they need to be consistent chunks. So I think overall, like the data consistency and like making the data from a provider standpoint into cubes and like acknowledging that these cloud access patterns, that they need this kind of like contiguous formatting and consistency with encoding, chunks, shape, all of that. I think from like a data formatting is the biggest hurdle was there that I found. But the actual access technology, I think, is moving really rapidly and is kind of reached a level where it's kind of waiting on the data for it to be really um, unlocked more by the user, because we're just limited by what the data is at this point, I think.
Yeah. Thank you. I think we have another question from my end, so hang on a little bit, Ayush. Thank you. That was a great response.
Yep.
Hi, this is Ethan Davis from Unidata. I guess in terms of data sets and granules or whatever not matching up chunk-wise or however, we've done a lot of our Unidata, we focus on real-time weather data, so we do a lot of operational data streams, and we've done data services over that for a long time and done some aggregating of data sets. And we moved from kind of index-based aggregations or whatever concatenations of granules to kind of a coordinate system based. And I think so in the thread server, it focuses more on that. And then also I know there's the CF conventions, there's a CF aggregation convention that's been developed over the last few years, and that also focuses on coordinate systems. I'm just wondering if where that comes into play or might come into play with this, and that seems, yeah, I mean, I think even fairly static and long-term data sets can have inconsistencies, but real-time operational stuff, you definitely have to worry about that. So I don't know,
Yeah.
I'm thinking this aggregation stuff needs a discussion, a bigger discussion just about that.
Yeah. I mean, so I haven't done the coordinate system aggregation you're talking about, but I have. So like this final data set on the right here, this is concatenated differently than just along like the standard coordinate system. This is by the SWAT data format specifically, where it has a cycle number and pass number concept. So it's stacked along those dimensions. Those are like like virtual dimensions almost. Like they're not part of the source data set, but they're kind of stacked along this way. So that's one approach I've tried to make it. But even this needs consistency. I mean, the other like swath dimensions still need to match. But yeah, the coordinate system one is interesting to look more into that.
Yeah, thank you, Ayush. We have one more question, maybe our last question for Ayush. That was a great answer. It's certainly there's not like a single solution for this. There's definitely like a need for an ongoing conversation. So hold on, Ayush.
Yeah.
Yeah, and what I would like to follow up, and I feel like the responsibility to follow up with this, right? It might be time, right, in this context of like, well, do we do this in index space or in projected coordinates or whatever? And I feel like I have to mention, maybe we need to think about representing location in a completely different way to begin with, right? Thinking of S2 geometry and stair, where these problems might actually be solved completely different, where we don't express the location by an index, where we don't express the location by a coordinate reference system, but project it into, well, a cube sphere or whatever it might be, and having a one-dimensional index that represents the location on different resolutions. So I hope that someday we, in the future, in the close future, we can get there.
Is this for like level 4 or level 2 data, like all of them, or just
Level 1 data, I guess. Level 1 and level 2 data, yeah.
Yeah. Okay.
Was there a question?
It was really common. It's just like, I hope we get there, right? Once we have that technically under control. It's like, if we have chunks that live somewhere and we can pull them out, let's now think about how we can represent location maybe in a different way.
How does that work in 3 or 4 dimensions?
Well, need different representation for all these additional dimensions as well.
I think this is like, I don't think there was a question for you, Ayush. I think that's just maybe a
Yeah,
a
no worries.
comment.
Really just a
Please do
follow-up.
not try to answer this.
Okay.
There was no
It's not
question.
up to you, Ayush.
Did the comment, yeah.
I think that's just part of the conversation, perhaps the reason to be here. Thank you,
Yeah.
Ayush. I think that was great. Thank you for presenting your work. I thought that was awesome. And Ayush has just started a new position, so yeah, so congratulations on that, and give another round of applause for Ayush, everybody. And do reach out to Ayush if you have more questions. I think this is an ongoing effort as well, that Ayush kind of spearheaded as well with the rest of a bunch of people from Virtualizer too. Okay, let's see. So I think I'm up next. So let's see if I go to Chrome browser. And then do I have to, that's it, right? I don't have to, yeah. So so this is not really a presentation I created. We invited Daniel Kaufman from one of the DACs. He's done some really interesting work over the last couple of months, kind of continuing along what Ayush did and just kind of like looking at the availability of DMR++ across different collections and the cloud. And this is an ongoing effort. I apologize, this is a PDF, so I'm going to have to scroll a little bit. He couldn't make it to the presentation, not even virtually, so he asked me to give a brief summary. This will be brief, just a couple of slides. I may not have the answers for what you might want to ask. I am familiar with this work, so I might be able to answer maybe very basic questions, but I would recommend if you do want to have an evolving conversation with Danny, to reach out to him via GitHub or his email. This is an ongoing effort from his part. So a little bit of the context for what he's looking at is he's looking at tempo data. This is a new setup that launched about a couple of years now. This is revolutionary in kind of like the way we think and measure and produce these air quality products. Tempo, this is one of the, here it is, so I apologize for the scrolling. And then the problem, the way he states it at least, is that you get these scans every hour, which creates around roughly 10 level 2 NetCDF files for level 2, 10, and then for a level 3, just one single file, or you can call them granules. Oh, I apologize. Let me make sure that it's being shared, the slides. This one. Okay, so I'm hoping that people can see now. Yeah, just confirmation in the room. Okay, yeah. Okay, thank you. So apologize for that. Right, so this is work by Daniel Kaufman. Here's just one more minute here for people to see email and GitHub accounts to reach out for the work he's been doing, which is really interesting. And again, the context is tempo data, air quality data, and one of the problems that he's looking into is level 2 data, which is essentially every hour you get 10 different files, NetCDF files, and every hour you get one level 3 data. And in this scenario, all of them have DMR++. DMR++, like I usually introduce, it's just kind of like this metadata sidecar files that OpenDAP kind of like produces on the fly, and it contains not only what's the information that is inside the NetCDF file or HDF5 or HDF4 file, but it also contains the ++ part, which is just a byte range, and essentially it's a bit of a chunk manifest. It's a map of where the chunks live within the file so that you can access that performantly. So he's looked roughly about a year's worth of tempo level 3 data. He's also looked at level 2 data, but I think he's just saying here, in terms of the problem is that for just the level 3 data, which is one file per day, you roughly get about 2.5 terabytes of data. And so the problem is like, how do you streamline the access to these NetCDF files that are sitting on cloud? And so he kind of took over to about what Ayush produced in terms of this functionality within Earth Access, which is that you can query, but also you can use internally these methods that called Open Virtual MF Dataset that include the DMR-PP or DMR++ parser and interrogates with Virtualizer and generate these chunk references. This, again, we're talking about the metadata translation and using engines to drive access to this collection of granules. What he found really quickly is that with level 3 data, with the work that Ayush did, was pretty straightforward to concatenate all of these 1,000, I think it was roughly 5,000 granules. Well, the level 2 data failed. And so there were some lessons learned about why these things fail in terms of the data, metadata translation. And some of the, in terms of the level 2 data, which was interesting because Ayush was also working in level 2 data, SWOT level 2. But this is in terms of tempo data, is that in that scenario, concatenation dimension is different length in some granules, and the presence of variable length chunks that are not permitted. It may have changed recently, but my understanding, according to his slides right now, that it's still not permitted within ZAR, or that ZAR model that's being used within the Earth axis, because there's a lot of evolving pieces here that get updated all the time. In terms of level 3 data, again, this is gridded data products and nice lat-long grid, so it was able to do that really successfully. And then you can open as chunk manifest quickly, roughly within 10 minutes, entire year of data. And with that, when you use this Earth Access Open Virtual MF data set. Without it, if you just use Earth Access to access all of these granules, it takes about a day, roughly 24 hours. So that's a pretty good performance boost right there. And so you want to see a little bit of the challenges, so a little bit of performance assessment. He has created some GitHub discussions in the Earth Access. And so you can, if you want to learn more, please go ahead and go to these links. I think we'll add all of these slides to the session doc. And so he also created this kind of like assessment in terms of availability of DMR++ across the DACs. And so taken for level 3 data, which is the scenario that did work. And it did work because the DMR++ are available and are up to date. Just for reference, DMR++ metadata sidecar files have been produced for many years, but they're continuously being updated. And so in this scenario for tempo level 3, which is a pretty recent data set, it worked really well because these are available and up to date. So one of the assessments he did in terms of all of the DACs, the NASA data, is to see, okay, so if DMR++ works, so how many collections out there that do have DMR++ that actually work right now without having to do anything to it? And so he found that this is a bit of a summary. I hope it's a little easy to read. I know, I apologize for like the sizes and everything of the text. But essentially, he found 13% of essentially the collections across the DACs. They all have, the 13% have cloud OpenDAP URLs available through the CMR, meaning that you can query and you will get cloud OpenDAP URLs. And that will essentially mean that they will be associated with DMR++. 4%, you're able to find DMR++ URLs without cloud OpenDAP URL necessarily. So that's a bit of an inconsistency of the database, more than anything. So that's a different kind of problem. He found 21% of the DMR++ file being downloadable, meaning that means that if you have the cloud OpenDAP URL and you append a .dmrpp, you're able to actually stream and download the DMR++ and check it and just parse it. And then of those 15%, of the total 15%, DMR++ are also openable by virtualizer parser, which means that essentially they can be parsed, which is still an evolving target, in which, again, it probably means that this inconsistency between these metadata translations and they're not necessarily up to date. Of all of the DACs, this graph with all of these column bars over there, essentially that was an assessment in terms of across all of the DACs, what is the presence of the DMR++ for each collection. You're just querying try to find one cloud OpenDAP URL or one DMR++ available for that, whatever count of collection. And so he found that most of collections do not provide DMR++, mostly because a lot of them are not cloud. The server is not on cloud. It's mostly on-premises, so this is a cloud service that OpenDAP does. And so a lot of the OpenDAP servers are on premises. And then so he did found that Justice and PODAP are the ones that are more consistently providing cloud OpenDAP service, which leads to this more availability of DMR++. And so as a result, as it is right now, then there's this evolving target or conversation about what if DMR++ and virtual data set aggregation it's possibly a workable solution as it is right now. But it will depend if you're able to find this DMR++ or Cloud Open App service. And so this is the last slide about evolving and current work that he's doing. And I'm just going to read about this. And so current work is just creating combined and essentially entire collection of reference file using virtualizer, so that in this scenario, rather than searching for DMR++ and then aggregating them, you can just do that once, and then you just store potentially as like a chunk JSON, and it will be a unified single reference that you already don't have to aggregate multiple times. And so in that case, that's for his work in Tempo Level 3 for that entire collection. And then so the status that he has success with the latest version of virtualizer. There was some issues with the group at the root level that he was having some problem that was solved in one of the previous releases of virtualizer. And then now that it's using also status of current work, just checking about upstore functionality that has been added in the latest release. Technical challenges, again, he found some technical challenges working with variable length chunk arrays for level 2 data. So this is still an evolving work that he's doing for level 2 data for the Tempo data set. And then there's some implementation decisions later that he's also working. So please, if you have questions for Daniel, reach out to him. You can find him on GitHub or via his email, and I'm sure he will appreciate any collaborations or any conversation spam from that. And if you guys have a question, I'm happy to try to answer it. Or if not, at least to record it for Danny. Yeah? We have a question, and I'm not, let me check on the chat.
Well, this time an actual question. So you guys had achieved 1 month worth of Tempo data in there. Is there some kind of indication at what point this might break? Like, is this scalable into infinity, or will these the sidecar files just explode at some point?
I think you might be talking about the aggregation of this into a single reference.
Yeah.
That's a good question. I don't know the answer to that. I know that that's a current work for him. I think these sidecar aggregations could reach gigabytes.
Yeah.
But that might be, in terms of DMR, PP, they're not really at the process of aggregating them right now. They're just per granule. And so I think that might be more about the question for the Kerchunk JSON,
Exactly.
kind of like metadata. If anybody has a better answer than that,
I can talk a little bit about it.
okay. So we have in the audience a little bit more of a reference for that from Joe. Yeah, please, Joe, take it away.
Yeah, I mean, we've seen many gigabytes at this point in a single Kerchunk reference. There's also, so Kerchunk supports JSON or Parquet. And then I'll talk in a little bit about IceChunk, which we support this concept of called manifest sharding, basically an arbitrary way to split the manifest. So at that point, you could essentially scale infinitely. Yeah.
Oh, that's great. Yeah. Thank you, Joe. Yeah. Any other questions that I can reroute to somebody else?
I think Alexander's up next.
All right, no further questions. I'm glad about that. But yeah, so do please reach out. Okay, so, oh no, from Joe.
I have a question. Can you, or maybe James, tell a little bit of the backstory of where DMR++ came from?
Sure.
It's been around for a while, I assume.
Okay, so here's the actual backstory. It started as a design group meeting at Ted Haberman and Aaron Robinson's condo at Copper Mountain in, I don't know, about 10 years ago. And it actually, its previous history before that was in HDF4 maps. So HDF4 is the precursor data format or meta format to HDF5, and the HDF group had developed this concept of mapping. And so we looked at that, and we looked at S3, and we realized that if S3 supported range gets, oh yes, it does, then we could effectively write a device driver for S3, and if we knew where the bytes were in the file, we could just read them and reassemble them, and that would be really easy. And we could do this with HDF5, and it had only had about 20 years of development, so it would be a real simple problem to solve. And so, so we started down this road, and that's where it comes from. And obviously, when the data are relatively simple and straightforward, it's very easy. But it turns out that that the HDF4 and HDF5 data models, the internal models, are actually extremely complicated, and the APIs are very complicated. But that's where it ultimately comes from. And it has always supported some concept of aggregation. The files, they're XML files because we're old and crufty, but whatever. They can associate a different URL with each chunk. But that's a kind of a problem in and of, I mean, it's both a good thing and it's also a bad thing, because in authentication systems, every URL has to be individually authenticated. And so it's much more efficient in general to have a large collection of chunks that you can reference and move around in larger blocks. And that's been a key component to performance in the overall system. But it means that these documents can easily reference information in multiple granules, which is the NASA term for a file in general. Got it, all right.
Okay, so that was a great question. Thank you, Joey, and the answer. Thank you, James. So up next, we have Alexander Jelinek, who's joining us remote. I'm going to stop sharing my screen. Alexander, I see you. Yeah, so when you're ready, take it away. Share your screen if you, can you share your screen right now? Maybe we might need to give you,
Says sharing is not turned on. Send the request.
okay.
I'm sending a request.
Okay, hold on
But
tight.
what my request being processed, since there was a question of historical background and story, I have the story. So I was one of the attendees of that meeting, Ted and Erin Conda at Copper Mountain. I was remote there though, but still. And so, yes, so the DMR++ came out of HDF groups and OpenDep's collaboration, I would say 2017 maybe. In 2020, I received a small grant from USGS. One person you may know maybe goes by the name Rich Signal. And out of that collaboration came out an implementation that I call the Z chunk store. And that was a JSON description of chunk locations for ZAR and X-ray. And then when I handed over that to Rich and the community, that later became Kerchunk. And so now we have that backstory as well. So
Yeah, thank you. Can you check if you can share the screen now, Alexander?
yes.
Great.
So here we go. So as you all mentioned, there is a lot of talk of HDF5 or NetCDF4 files as being sort of the sources of chunks. And this talk is about cloud optimized HDF5 files. I also would suggest to, as a way to avoid ambiguous any ambiguity, that when people talk about variable length chunks, I think what they actually think is variable shape chunks. And the reason why I'm suggesting this variable shape term is because variable length, there is a category of data types called variable length. And maybe sometimes that may confuse some people. But if you say variable shape chunk, then I think it's exactly what we're talking about. So cloud optimized HDF5 file. It's the same idea as cloud optimized GeoTIFF. There is a binary file format called HDF5, and the internal layout of those bytes, by default settings of HDF5 library is not cloud optimized. In other words, forces way too many requests for various pieces of file. And so the idea of cloud optimized file is to find techniques that you can basically reorganize those bytes. Same file, nothing changes as far as the validity of the file. It's just that they are organized in a way that there are not that many requests. The goal is that those files, as they start hopefully become available in the not so distant future, they are going to be this nice helping foundation to all this other work and capabilities that are being talked to at this session. As far as I know, for example, ISET 2 ATL03 product, release 7, I heard at this conference that that's already cloud optimized HDFI files. What also I know is that nicer satellite, which is going to be launched maybe end of this month, maybe a couple of weeks later, is going to come out completely with cloud optimized HDFI files. So in a couple of years, you may have more cloud optimized HDFI files than all the entire current as this archive of HDFI files. Who knows? Anyway, so I'm going to skip some things. So this is the important point. So what makes a cloud optimized HDFI file? And I think number one, and the most important thing is increasing the size of a data set chunk. And when I say data set in HDFI world, that means ZAR array or netcdf variable. So, and when I say chunk size, I mean size in bytes. So I'm very careful. So if I'm talking about chunk shape, then I'm talking about how many elements in each dimension of a chunk. So why so far no one really wanted to produce bigger chunks? I guess because they were spoiled by really high performance of the modern file systems. So said, I don't care. But now, of course, when you move into cloud object storage, it really matters, because effectively chunk is immutable atomic amount of data, and whether or not you like it, you kind of have to process them separately and individually because they're usually compressed. And so number one, and the most important, larger data set chunk sizes, as much as it makes sense when you produce a file, because these files are produced in near real time, so there is no really understanding of the future data. But again, within a file, definitely they should be bigger. And I was telling some people, again, 1-2 megabytes at least, see how it goes. The number 2 step is to consolidate internal file metadata. And this one really is handy if ever in the future of those files existing, someone comes up and says, well, we kind of need some accurate information about something in that file that has not been captured by all these other alternative ways of describing file content. Maybe it's going to happen, maybe it won't, who knows. In those kind of cases, or if the file is immediately appeared in a S3 bucket, then being able to quickly scan the information about what's in the file and where it is, that's where the consolidated internal file metadata comes really and shines. The last one, luckily, at least in NASA satellite data, there is no lot of use of variable length data. That's why I was careful and saying variable shape and variable length. So there is variable length data types in HDF5. And so there is no that much variable length data types in those files. You can use them in attributes, that's fine, but not in the HDF5 dataset or in arrays, because it complicates X. So that's what makes cloud optimized HDF5 file. The method, how you can produce chunk sizes larger, essentially, you first have to think about the chunk cache size of the HDF5 dataset that you are creating. The next release of the library, because of this issue specifically, that's the next version 2.0 due September this year, will come with default size of these chunk caches of 8 MB. So theoretically speaking, all the chunk sizes up to 8 MB should not impact the performance. For anything larger, you would have to increase yourself this chunk cache size. Otherwise, really writing out is tough. Next, I don't want to, again, go into too much details here. As I said, variable length data types, try to avoid them. Most of the time, I don't see them, but if someone knows of them, I would like to hear about those files, and I could like to take a look and see how it goes. But other than that, I think it's safer to go. Where this risk may creep in is netcdf4 strings, because netcdf4 strings are stored as HDF5 variable length strings. So if you have a netcdf4 string variable, then you basically have this variable length data in a file. Luckily, again, no one stores a lot of strings. And since someone was talking about what I understood as digital global grid systems, DGGS, if you do zone IDs and some zone IDs come at strings, then I definitely suggest not using variable length strings because that's going to be very useful data that should not be in a variable length data type. So ways to consolidate internal file metadata. Again, there are a couple of ways of doing it. Number one here really is the best because it helps both the HDF5 library and all the other tools that I mentioned. Number two here doesn't help the library as much, but again, still should be good for the other tools. And the third one is essentially treating an HDF5 file and its content essentially just like a opaque container. You slap whatever description of the file content into what's called HDF5 user block. It is at the beginning of the file. And therefore, whenever you read it, you start from the beginning of the file, you grab a couple of megabytes. Hopefully there should be enough to grab the entire user block. You can find where the user block ends, and then you process that information in the user block any which way you want. And so those are the three ways to do it. The number one, as I say, has shown to yield a slight increase in the file sizes. When we worked with the ISA2ATL03, there was about, I think average was 0.4 or something percent increase in the average increase in the file size. But that was deemed to be essentially a non-issue to gain the performance boost. So again, lots of here information here. This page aggregation is not the default. Someone has to do it and say to the library. It's not going to ever become a default of the library because again, all the other applications that do not really want to have their files in or don't need to have files in object storage don't want to have to do it vice versa. So this is something that applications thinking about those HDF5 files going into object storage will need to do. Yeah, you have to create files with that set, but that's pretty much like the same story with cloud optimized geotiff. You had to generate a new geotiff. And again, if you get this page size, that's the whole point of this approach. You basically are telling the library, stop thinking where is something going into the file. You have a specific file page size, and you just fill this file page size. And once you end filling this file page size, you create another one, and then keep doing that stuff. And the library splits the types of data that goes into these pages. There is a internal information pages, and there is the data page. And so, again, if you are lucky and your file is not that complicated, or even if it's a complicated, you're probably going to end up with one page or maybe a second page with internal information that will be needed to generate something like Kerchunk JSON or DMR++ file, sidecar file. There are cases, again, that I run public, they're all up to 7 file pages, but those are files with thousands of HDF5 datasets and very unique. So that's that approach. The other one, again, I'm just going to, how much by time? Couple of minutes? All right, I'll keep going until someone mutes me. FileMate metadata block size is another one where, again, the library writes data as before as the original default setting. However, there is a block of bytes in the file reserved for, again, internal information. And so in this case, you do not get any increase in the file size that you would sort of have just because of having these file pages. but metadata block cache kind of gets filled in. And again, you get the benefit of consolidated metadata. And that's pretty much where I would stop, unless there is some need for talking a bit more. Okay.
Yeah, thank you, Alexander. Yeah, that's very much. Yeah, appreciate it. Thank you very much. And with that, a question or two from the audience members. And I see a hand raise. Hold on tight, Alexander.
Hey, Alexander, this is Ethan. I just wanted to ask about the string in netcdf4. What does HDF5 have for strings? Does it have non-VLAN strings, and we just happen to choose the wrong one?
Well, I wouldn't say wrong at the time of choosing. So there are 12 different ways how you can store strings in HDF5. There are 2 encodings, UTF-8 and ASCII. There are fixed length and variable length, and then there are 3 ways you can end the string: null terminated, null padded, and space padded. So I would say that my choice of serious data, again, what goes into HDF5 dataset or netcdf variables, I would say it should be UTF-8, fixed length, in other words, fixed number of bytes, and null terminated.
And null terminated, yeah.
Yeah.
All right, thanks.
You're welcome.
Another question from the, oh yeah, I see a hand raised. So from Joe, take it away, Joe.
This is Joe Hammond, and this is both, there's a slide coming up that I want to ask in my talk that I want you to see, like look at, and then tell me in a little bit. The question is really, how much should we expect the traffic to decrease? So basically, like one of the problems with using standard HDF5 files in the cloud is that if you use them as a file, like with a virtual file handle, you end up with many more range gets to find arrays and metadata and that sort of thing. You have to scan around the file a lot. Do you have an idea of roughly how much of an improvement we should see in the traffic pattern against HDF files in the cloud going forward?
From the cases that I've been involved in, for example, just for generating something like a chunk, you had a reduction from 6,000 plus to about 2 requests. When you come reading the data for these paged files, paged aggregated files, it really depends where the chunks of that specific array are. So very often you can have all the chunks in a single page. So it's 1 read, or maybe 2 for the data arrays that are really large and comprise sort of a large part of that file. Then might be more. But again, it's typically, instead of requests for each chunk, you're now reading file page, and so conceptually, it's like a ZAR shard that you read instead of each chunk.
Okay.
Thank you. Any other question before our next speaker? Well, I do have a question to you, Alexander, mostly from the user side. Is there, with all the work that you're doing, really cool work that you guys are doing, is there like some form of API or maybe recommendations that someone who's not as savvy can maybe produce data that will be some form of optimized, that it's not too complicated to kind of like jump in and start using those, whether it's recommendations or guidelines on your libraries, so that this data has a fast access on the cloud?
I know that I think Cloud Native Geospatial Foundation wrote some kind of a document that talks about cloud optimized netcdf4 and HDF5. I can also say that in my capacity as a co-chair of this dataset interoperability working group, my plan is for the next sort of 12 months, I initiate the work on producing cloud optimized guidelines for NASA Earth science data producers, and also cloud optimized as in that kind of, how to set settings for the software, but also introduce ideas of more advanced compression methods being also used so that we get maybe more chunks in a, smaller but bigger, or at least faster to decompress and that kind of thing. So that's sort of my plan in the next 12 months, but nothing exists right now.
Okay. Well, thank you. Thank you very much, Alexander. Again, maybe another round of applause to our speaker.
Thank you.
And with that, I had the pleasure to introduce Joe Hammond here for our last speaker. Yeah, take it away.
So we have to share, right?
On the one on the right.
Okay, here. This thing. Here, slideshow. All right, great. Well, hi, everyone. My name is Joe Hammond, the CTO, co-founder at EarthMover. I work on X-Ray, ZAR, Ice Chunk, a few other projects that are relevant here. So yeah, I'm going to talk about, I'm going to start by motivating this. I'm not going to jump straight into all of this. I'm going to try to motivate why I think that what we're talking about in this room today is important. And then I'm going to end the presentation by talking about kind of some of the progress we're making on both the X-Ray and ZAR side, but also on our new project, Ice Chunk. Okay, so this is where I think we're going. And I mean this truly, and I actually think this might already work today to some extent. But AI agents are taking workloads that typically we use human brains for and are being automated. And I think you could almost do this today with Claude, which is to say, tell an AI agent using the latest atmospheric reanalysis from NOAA, I don't know what that is, but let's see what it comes up. Calculate the likelihood of extreme heat, 110 degrees or more in Seattle, and then go out and do some data analysis, right? I think a bunch of us in the room know how to do this. It's kind of startling to know that there's now AI agents that could do this for us too. But I like to think about this as a motivating use case, because what does it take for an agent to be able to do this, right? You have to have access to the data. This might take a lot of computing power. It might need fast access, or at least scalable access to that data. So this is the sort of stuff we're trying to solve at EarthMovers. So we're a relatively new startup working in this space with a mission to empower people to solve humanity's greatest challenges, working with scientific data. Started the company with Ryan Abernathy, many of you know, after working on the Pangeo project, X-Ray, and ZAR for a number of years. So we, like I said, work on a bunch of open source projects in this space. You've heard about all of them in this session already, so X-Ray, ZAR, and Ice Chunk. Today I'm going to zoom into the Ice Chunk stage of space on how Ice Chunk does virtual data specifically. But I do also want to say, I think that these are important parts of how we would, I believe if you told Claude to go and do that problem that I mentioned, it would use at least a couple of these tools, which is pretty cool. So when I think about AI-ready data and tooling, I basically break it down into building blocks. I'm going to assert that we need three. One is that we need highly scalable cloud data access, so the ability to stream data directly from cloud storage into some computing. We need some catalog that is an API, essentially, some ability to stream, to find data programmatically. And then we need our data formats to be cloud native and self-describing. So this is all stuff we've basically been talking about today. We've seen various examples of it. I think we all know what cloud object storage is and its potential, so I won't spend a lot of time here, just to say that it's a real enabler for federated access, automated access, that sort of thing, not having to download data. We take that for granted, but just a few years ago, there was still a lot of download first architecture is being advanced. So I think we're making progress there. Okay, next is this idea of kind of a central programmatic data catalog. And here I really am trying to push forward on this idea that like data catalogs as APIs. Like we have to move past this idea of like billboards as metadata catalogs, but we need to be able to like directly take them. So I have some good examples here, stack, an XPy stack, basically directly into X-ray objects. We saw some great examples from Earth Access earlier, directly into X-ray. And then here's an example using ArrayLake, our company's product. Basically, it's really fuzzy, at least for me on here, but hopefully those online can see it better. But being able to search by metadata and directly open that data using X-ray. And this is the sort of thing an AI agent could figure out how to do and operationalize without intervention from a human, which is pretty cool. Okay, most of the rest of my talk is going to be kind of pushing down on what I think is the hardest part in all of this, which is connecting the data that we have to this concept of self-describing cloud-native data formats. We have hundreds of petabytes of data today. A lot of it's sitting in the cloud. A lot of it's not available through a cloud-native access pattern. And so I think that's one of the areas we're trying to solve in this session. So first off, I think it's worth noting that we've made a bunch of progress in recent years. I think ZAR, this kind of idea that like I can just point X-ray at ZAR available over the public internet and like get a data set back, and then in a few lines of code make a plot, do some analysis that's meaningful. Here I'm pointing at a dynamical URL to his public ZAR store, and this runs in a few seconds on my laptop. And I do some analysis about some 2-meter air temperature or something. So users love this. We should figure out ways to make this sort of thing easier and easier. And then in terms of virtualization, so virtualization, we're going to talk more about how I think of virtualization here, but it's possible to obtain that cloud native behavior on top of archival data. So this is data that's already in the cloud, not formatted as cloud native, a cloud native container. It's possible. There are challenges with that though. One of the challenges with this idea of like cloud native formats is that data providers have been really hesitant to leave behind traditional data formats. And part of that is funding, resources, like there's already stuff in flight, that sort of thing. But also like there are some drawbacks to some of these cloud native formats that make it hard for data providers. And as we've heard, not all data sets can be virtualized. And then there's all these gotchas along the way. So things like chunking and encoding and et cetera, et cetera. Okay, if you've been here at this conference all week, which I haven't, today's my first and last day here, but you've hopefully seen a couple talks that cover a good chunk of what I was going to talk about, so I'm going to get to zoom in. But Lindsay on our team gave a talk on ZAR and Ice Chunk already. Quick show of hands, who saw that? Great, okay. Most people in the room already got to see that, but Lindsay's sitting here. Go find her afterwards if you have questions about those topics. And then Max gave a talk on virtualized ZAR. Max is also in the back of the room here. So virtualized ZAR just had its 2.0 release this week. That project's really advancing our ability to generate virtual data sets and work with them in the cloud. I want to say a couple things about what I kind of think of as the promise of virtualization. So, Kerchunk, DMR++, virtualized R, I think they're teaching us some things about what's possible here. The first observation is that basically all scientific data formats, multidimensional array formats, are the same under the hood. They have some metadata in them describing the groups and arrays. And then they have a collection of compressed chunks. They don't have to be compressed, but optionally compressed. And this sounds a lot like ZAR, actually. And so here on the right, I'm showing you kind of what the architecture of a ZAR group would look like. You have some sidecar files, these zar.json files, and then you have a set of chunks. And in Zar, we spread those out across different objects in S3, and in an HDF file, they're all packed into one object. But fundamentally, we can represent an HDF5 file as a ZAR file in many cases. And so that mapping from an archival format to the ZAR API is what I think of when I think of virtualization, basically allowing us to virtually represent these archival formats as cloud native containers. And these doing this can deliver huge performance gains. And so just here's an example of what sort of gains these can deliver. And so here is a little benchmark just using off-the-shelf tools. And I think it really hits home that the cloud object storage is not a file system. And if the file format you're using requires being able to seek around the file to find different bits of metadata, it's really expensive to use that. And so on the left, we have a netcdf5 or netcdf4 file using h5 netcdf with some Python magic to open it as a file object. And you see to open and load this 1 gigabyte data set required 500 HTTP requests. And then for ZAR, just vanilla ZAR, 150 or something like that. If you consolidate that metadata down, you can get down to essentially 1 request, right? And then I think IceChunk had 2 or 3 in this stack. So basically, we've figured out some ways to reduce the amount of traffic needed. And of course, that all translates into performance in terms of loading as well. So what does it look like to actually implement a virtualization workflow to generate a virtual data set? And so that process looks typically like this. You identify some archival file, some granule. You scan or index that file once, and you record the metadata and the locations of those chunks. So set those aside for a second. You maybe could then go combine that metadata and chunk locations with other files. That's what we've been talking about for aggregation. And then we save that metadata somewhere. So Kerchunk makes it possible for you to save those chunk manifests and metadata in either JSON or Parquet. So there's a spec for those. DMR++ helps you or uses XML, right? So in both cases, there's sidecar files that then you kind of keep around with your data set. But in talking to people, often get the question like, how do you actually operationally manage, update, and version massive archives of these virtual references? And adding a sidecar file to your cloud repository, you double the amount of files you have. It's more things to keep track of, potential for things to get out of sync, et cetera, et cetera. So this is where IceChunk comes in. And so if I do that, you get the IceChunk logo. I'm going to zoom in a little bit on how we do virtual data in IceChunk now. So first, if you missed Lindsay's talk earlier in the week on what IceChunk is, it's a new transactional cloud-native storage engine for ZAR. So unpack a little bit of what that means. ACID transactions, the ability to atomically evolve the state of a ZAR store is something that is missing from the standard ZAR spec, and so IceChunk brings that. Along with that, it brings the concept of data version control, so the ability to do time travel and snapshots. Supports many of the same version control concepts that are in Git. So you have branches, tags, and commits. And it also supports virtual data sets. So this is the chunk reference stuff that we'll talk more about. It's written in Rust, so it's super high performance, and it's open source. It's Apache 2 licensed. Give an idea on the performance piece here. So we did a pilot late last year, early this year with NASA, looking at the GPM iMerge data set. the task was to extract a 1-month time series from 1,488 granules. So big stack of pancakes. We're trying to pull one time series out of them. This is implemented today using Giovanni on-prem. And essentially, they're trying to figure out how to do that same thing in the cloud. And what I'm showing on the right, the 2 time series are just showing that we're able to pull the same data from Giovanni and from IceChunk. But the takeaway is that we went from 45 seconds down to 3 for this time series extraction, which 45 seconds for a time series extraction is kind of a non-starter for an application like Giovanni. And so in our first pass, we were able to improve that by 15x. And I think this speaks to the potential of what virtualization can do. Okay, so I'm going to get nerdy for a second and explain what's happening under the hood inside of an IceChunk repository and how it works. So IceChunk is a backend for ZAR, and it stores the components of a ZAR store in its own specification. And so the way that works is we have a collection of different files inside of the root of the repository. And so you have reference files. Those are like branch pointers, for example. So that's this top here. And then those all point to a set of snapshot files. And the snapshot includes one or more chunk manifests. And then the chunk manifests point to actual chunks. And those chunks are actually ZAR chunks, or they could be chunks inside of an HDF or NetCDF file. And so it's this architecture that we use for native ZAR data in IceChunk and for virtualized data. And what we have is a really flexible specification that allows us to store both of these in the same way. And so a little bit more on how this works. All chunks are recorded in a manifest in IceChunk. So this enables virtual references. And it's how the ACID transaction and version control features work. And so adding or modifying virtual references in IceChunk is the same as updating native ZAR data in IceChunk. Only you don't write for virtual data, you don't write the chunk to the chunks directory inside the repository. And then finally, one really interesting feature that this enables is you can ingest data via a virtual ingest process and then edit or update the metadata about that data set afterwards without impacting the original virtual or archival data set. And so this allows you to say, oh, I found an error in the metadata, I want to change that, but without having to change the original granule. So it allows you to evolve the state of a data set without either the metadata or the chunks without having to rewrite the original granule. Okay, so a couple conclusions. We can achieve this AI-ready data future by putting data in the cloud. We're already doing that. Using cloud-optimized self-describing formats, things like ZAR, and that we can that we need to go beyond metadata catalogs towards catalog APIs. We're doing that in some cases too. Huge challenge ahead of us is getting the hundreds of petabytes of Earth science data that exist today into this cloud-optimized form. Virtualization can help with that. And then finally, IceChunk offers a high-performance transactional database for virtual references. And by the way, we released IceChunk 1.0 just 2 weeks ago, and there's a link to the blog post announcing that. Yeah, and that's it. I'm going to leave the QR code here for the blog post. Yeah.
Any questions for you? How about the virtual
Technology is above me, so I'm just going to ask a question about the challenges we always face. So if you are dealing with the data collections that use different variable names and it's not standardized, how would you know, let's say when you go tell the Cloudy to find the data files for the temperature of Seattle to do analysis, how do you know they actually find the right files? Because, for example, temperature at 2 meters for atmospheric temperature, and the variables in individual collections might be very different. So how do you know it finds the right thing and integrated it in the right way? In terms the, discipline is entirely different animal. So this is just talking about the variable difference.
I think it's this, I think the logic there, I mean, how would you do it, right? I think you would probably look at the metadata and you'd say, oh, there's a standard name in the metadata for this variable. It says air temperature at 2 meters or something. I don't know what the standard name is. But we have metadata conventions for this. And so I think the point of the reason I really pushed on self-describing formats is that, with the metadata attached to them, you should be able to, you or an AI agent should be able to find your way to figuring out what the right field is for the analysis you're doing.
Yeah, that's what I'm trying to really push for, standard way of describing things.
Sure.
Because
But
you
we
can be self-describing,
Yeah.
but not in the standard way. Human can understand, but machine may not. If it's not in the standard way. Because I could say my temperature.
I think we should use metadata conventions then, is my answer. Other questions?
Any other questions from the audience? Anyone from Zoom? James?
I don't see any, no.
We're getting very close to lunch now. So
Very close to lunch.
Maybe one question for you, Joe. So I'm trying to wrap my head around ice chunk. And so my understanding is that if you have something that fits the SAR data model, that means you can use ice chunk. Is that correct? As a premise?
as a premise, yes.
Okay.
Yeah.
And so if there's data files or variables that are inside a HDF4 or something that currently do not fit the SAR model, then my question has to do with more like this. I see this amazing thing about convergence of APIs, like XRA, for example, which is what you were talking about. And so we're approaching that, which I think is great. But then there's still parts of data types or maybe certain aspects of data that's still out there or being developed or incorporated might not be currently within the SAR model. And so my question to you will be, as we want to see some convergence of API, is the approach just to expand the SAR model, or do you think expand the virtualization model? What's the route for people who might not be on the SAR world, who want to ensure that agents or people who are more familiar? We're talking about interoperability, so maybe it's not a very specific question, but more like a broad.
Sure. I mean, there's definitely opportunities for us to expand the ZAR model. It's very flexible. I think that there's relatively few. I mean, you can put tables in ZAR, you can put strings in ZAR. There's a lot you can do there. So I think on that front, there's maybe technical things we need to advance. The Ice Chunk also has just on Ice Chunk in particular, it's right now we've implemented a ZAR interface. But the architecture of the project itself could implement other interfaces as well, and so there's nothing ZAR specific there except that it allows us to. We've exposed a ZAR API for it, and so we could do this for other data types as well. There's a question. Yeah.
Thank you. Okay, great. It sounds like Alexander has a follow-up or additional question.
I just have a question. So in iChunk, I noticed that what used to be JSON metadata, ZAR metadata, is now flat buffer. Flat buffers, I'm not sure about flat buffer format. Is that What was the reason for that? I thought that a lot of people like JSON just because they could look at it. So I'm assuming there must be a performance for just the size
Yeah.
of this JSON. Yeah.
Yeah, I mean, so yeah, the chunk manifests are in iChunk today are a flat buffer, and that's largely for performance reasons. We had the design target there was arrays with trillions of chunks, and there's also the ability for us to shard across, those chunk manifests, and so under the hood, we don't expect people to actually interact with each of those manifests individually, just as, there's the manifest or the metadata inside an HDF5 file is not necessarily meant to be consumed by anything other than the HDF5 API.
And yet here we are. Here we are.
Here we are. I know. So yeah, but it was largely a performance optimization. And we actually tried a few things. That's where we're at today, but I wouldn't be surprised if that particular design decision evolves over time.
All right, thank you.
Cool.
Any other questions? Hey, before we go, I want to jump in and say something and make sure that the people online hear it too.
Go for it.
So there's this Google Doc, and you all should put your names and email addresses, or at least your names in there, so that we can get in touch with you, because clearly we don't have time for 45 minutes of breakout sessions because we've got hunger and so on and so forth. But we will attempt to form a ESIP cluster around the notion of developing these standards. And it would be really great if you are interested, if you want to participate. It would be great to have Earth Movers' participation in this. It would be great to have Unidata's participation in this, and all of the other folks, Development Seed, all this stuff. Because we're all sort of nibbling away, just like Joe said, we're sort of nibbling away at the same problem, and we might as well not, make the same mistakes as other people have already made and learned about. We also have to realize that things like those varying length strings, yeah, those are real. And remember, just NASA has over 1 billion granules, okay? That's what they have now. And so we didn't even touch on HDF4 and HDF4 EOS 2, which actually houses some really important data. And that funny meeting that I was talking about at the condo, and Alexander was there, and a few other people.
Wasn't funny at all. It was very serious. And
yeah, it was
that's how I
terribly
remember.
serious. And some of us got altitude sickness. It was quite the whole thing. Anyways, at that point, the person who sort of started it all off, his name was Chris Linus, he said, "We don't care about HDF4." And I thought, really? And so a couple years ago, they said, yeah, we care about HDF4, and it turns out HDF4 is extremely complicated. So we have this historical data. It's extraordinarily important, but we want to bring it into the future, and that's definitely part of this problem. And when we think about standardization, we don't want to just think about how we do all the cool new things, but we also want to think about how these organizations adopt these standards. It's not just people, right? But it's these huge organizations that have complicated machinery they need to get going. So anyways, that's your challenge. Put your name, email address, all that other stuff, your pronouns, in the Google Doc, and so we can bring this together. And thank you very much.
Yeah, and thank you again to the speakers. Another round of applause, both in person and digital. Thank Ayush and Alexander.
Thank you all for coming and
being here.
listening to this very, very technical session. Nothing, Joe, nothing you said was even touched on nerdy in my book. So.
I said flat buffer at one point.
You did say flat buffer. Oh, my word. And thank you very much for the online speakers, too, and attendees.
Take care, guys.